I'll give it 1 minute and then I'll go ahead and get started. So to start with, I'll go ahead and go over the things that are happening this week. So today you have the quiz that you need to be doing. Monday was the electromagnetism CER. That was a student's choice. What is this down here? I'm seeing several things here at the same time. Oh, I see the other whiteboards behind this one. This one is suggested, the study guide. Of course, that's good to do. We went over that on Monday. Here we have the circuits quiz that's due today. Next, we have the lab. That's Faraday's inquiry stations. That's due Friday. And again, that's a student choice. You go ahead and look at all of the videos that are there. I have not posted that yet. I'm still waiting on 2 videos, but I'll post it by the end of today. So that is due on Friday. And then there's the extra credit. And remember, the extra credit is only for students that have done everything for the work. So today we're going over Earth's magnetic field. So let me go ahead and start talking about what is Earth's magnetic field. Uh-oh. I had pulled up the wrong thing here. Okay, so let's talk about the North and the South Pole. We always say the North Pole, that's like up above North America, but in fact, that is the magnetic South Pole. The needle on your compass is pointing to it's attracted to the South Pole because that's the north end of the compass needle. So that is attracted to the actual South magnetic pole. So geographic and magnetic poles are different. So in fact, the Earth looks something like this, as if there is a magnetic, a bar magnet running through the Earth. And this is going from, it's an area, it used to be, so let me say this, that the magnetic pole of the Earth has been shifting. So it used to be in Hudson Bay, Canada, at Ellesmere Island. That's maybe 10 years ago, maybe 15. And it's been shifting about 30 kilometers a year, which is actually a pretty decent amount. Now it's out of the Canadian Arctic Circle and it's moving towards Russia. So it's moving further every year. So it looks a little bit different depending on the time period. Through geologic time, we know that it's shifting because when we look at rocks that have been in Earth's crust for a period of time, so we're looking back in time at the history of the Earth, we can see that the iron in those rocks is aligned with the magnetic field at that time. So we know that it has been shifting. So what causes Earth's magnetic field? So we don't exactly know for sure. There are some ideas on what causes the magnetic field. And one idea is about the convection currents in Earth. Let's see, I think that's this one. So if you remember from an earth science class that you've had maybe in middle school, And again, my artwork is not terrific, but this is supposed to be the oceans, and then the black is the continents of the earth. And here we've sliced a piece out of the earth. So we're looking at this red that's in the very middle. That would be the solid inner core. And that deserves another conversation, because as to how solid that is, it, it depends on who you're talking to. Then the next layer, this is the liquid outer core. So that's liquid. That's like a lava type of a fluid. And this is metallic. So you have some metal in there. We know that when you have a current, that current induces a magnetic field. So if you have moving metal that is happening in this liquid here, then it is producing a magnetic field. Now, why is this liquid moving? It's hotter at the core of the earth. So we know that heat rises. So this liquid is rising, and then as it rises, it's cooling off. So then it cycles back down again. Okay, back down to the core of the earth. And there are some people that are saying that the cooler part of this liquid, some of it starts to solidify. So, in fact, the core of the earth, the iron core, is growing, not a lot, but it is growing. And so that is affecting the magnetic field of the earth. This next layer is your mantle. So we talk a lot about the mantle when we're talking about geology. And then this tiny, tiny little strip on the very edge, that's the crust of the earth. So all of this is happening very deep within the earth. Now, just that convection cycle itself um, isn't going to be totally responsible for a magnetic field surrounding the Earth. But when we add that to the Coriolis effect, so the Coriolis effect is due to the spinning of the Earth, that the currents cause forces that are acting on the Earth. Well, they're also acting within the Earth. And when we add that to the convection cycles from the heat rising from the radioactive decay at Earth's core, then that's one possible explanation for Earth having a magnetic field. Another thing that we know about Earth's magnetic field is that we have pole reversals. So right now, north is up here, south is down here. But over historical period of the earth, they flip so that this is south and this is north. It has happened hundreds of times in the last 5 million years, most recently 700,000 years ago. Typically, this happens every 250,000 years. So it seems like we're due for a pole reversal. And we'll talk a little bit in a few minutes about what are some indications that maybe that is happening. And there's also historical evidence that, or geologic evidence, that the magnetic field was actually turned off for 10 to 20,000 years, about 1 million years ago. So right now we are experiencing a 5% decrease in the strength of the magnetic field of the Earth. So that is the first step in showing that there is evidence that the magnetic field is indeed reversing. First, it weakens at the surface of the earth, but it also weakens on the surface of the outer core. Then you're getting islands of reverse poles. And right now, there is evidence that there is one of these islands beneath the South Atlantic Ocean. And so that means that the poles are reversed on that island that's at the bottom of the Atlantic Ocean. After there are the weakening of Earth's magnetic field, there are some of these islands popping up where the poles have reversed, then it actually flips. So some of the evidence that we have, not only has the magnetic field degree decreased, but on the surface of the Earth, so that's the bottom of the ocean, that's still the surface, right? We have an island, and I cannot say for sure, but I believe there are other small islands and these small pockets of reversed magnetic fields. Um, so that's about flipping the magnetic fields of Earth. If you want to see an animation of that, you need to go to Nova. Nova has a really cool, you have a whole sequence about Earth's magnetic field. So go look at that and look at the pole reversals. It's really very cool. So, what do the magnetic fields do for us? One of the main things is that it protects us from the solar winds. So, you may be familiar with the solar winds. So, that's energy that is hitting Earth's surface from the sun. And it sounds like, oh, that we need that. We want our plants to grow. We want the energy from the sun. We want to be warmer than if there was no sun. Well, yes, this is true. We do need some of that energy making it through our magnetosphere to Earth's surface so that we can have life on Earth. But these high energy particles that are thrown out from the surface of the sun, they're moving not only at 618 kilometers a second, but they're very high energy particles. So this is plasma. Plasma is our fourth state of matter. We know we have solid, liquid, gas, but plasma is superheated matter. And that means that it's in a state that we don't even have a nucleus that's bound. The protons and the electrons are charged particles and they're separate, and they're in this fluid type thing like a gel or lava type matter, that there are not molecules, it's charged matter. So you have positives and negatives all over the place, and this is called plasma. um, we also know that um, by the time those particles reach Earth, they've slowed down. Anything that it bombards on the way to Earth slows it down. So now it's only going about 400 kilometers a second. And these charged particles interact with our magnetosphere. Let me see, I believe I did my best to draw the solar winds here. And again, Nova has some nice stuff on this. And there are other resources as well. But here's Earth. And when we draw Earth's magnetic field, we draw it nice and round. And that is what's happening close to the surface. But where the sun is meeting it, there's a lot of force coming from the solar winds. So that force is really pushing on this. So it's constantly changing the shape of that magnetic field because, the Earth is moving, right? It's turning. So there's always a change in the direction that the Earth is facing the sun. So this magnetic field is constantly being flattened on this side, and it's being stretched out on this other side. So those charged particles hop along the train tracks. And of course, they're not train tracks, but this is a magnetic field. And the charge is going to follow those magnetic fields either to the North Pole or the South Pole. And that's where they leak in to our atmosphere. When they do get into our atmosphere, that's when we have the northern lights or the southern lights, the aurora borealis or the southern australis, that's at the south pole. The aurora borealis are at the north pole, the southern australis at the south pole. And those are 2,500-mile wide rings of where the electrons and the protons are colliding with different things in our atmosphere. So we know that when oxygen is 150 miles above Earth's surface and it's colliding with these charged particles, that's when they're red. That's when the borealis or the australis, that's when they're red or maybe going in the yellow direction. Green, the yellow green or the green color, is when oxygen is closer to Earth's surface, and blue is the color that we get when we have nitrogen that is 60 miles above Earth's surface. Now, the aurora borealis, the aurora, have different shapes, but those shapes are really dependent on the observer's point of view. So we can have corona shape, we can have rays, spirals, and arcs. They are most frequent. We don't know why, but we do know that they are most frequent around the spring and the fall equinoxes. That's the day right in the middle of the season. That's when they are most frequent. Like I said, we don't know why. We also know that other planets have these events. We've been able to, I think it's it's UV that we can use to see them, not only Earth's, but also other planets. So we know that Venus, Saturn, Uranus, and Neptune, they all have auroras, and also their moons have auroras. So, what do we need in order for an aurora to occur? That's a magnetic field and an atmosphere. Those are the two things that are required. Now, there's an interesting side note here that Jupiter's moon Io does not have an atmosphere. So, then according to the requirements to have an aurora, we would say, well, they're not going to experience aurora. But in fact, they do have active volcanoes. So those active volcanoes create a temporary atmosphere, and that temporary atmosphere can induce a the aurora temporarily. They're not permanent, but they are temporary. So I find that something that's really interesting. Seems like I've missed a portion here about the solar flares. Okay, so the energy that we're getting from the sun, some of that leaks into what we call the Van Allen radiation belts. I don't know a lot about the Van Allen radiation belts. When I used to teach earth science, I knew more, but I can't remember. But they are donut shaped. They surround the earth. The inner, so there are two radiation belts. There's an inner and an outer. So the inner is about 200 to 5,000 kilometers above Earth's surface. And that is filled mainly with these protons from the solar winds that have leaked into our atmosphere. So those have collected in that Van Allen belt, the inner Van Allen belt. And then the outer Van Allen belt, that's further above the surface of the earth. That's around 16,000 kilometers above the earth. And it's about 6,000 kilometers thick. that is mostly electrons. So we kind of see something happening similar to what's happening within a cell, that we have the protons closer to the center and the electrons further away, and they're separated. Um, don't know a lot about why that is the way that it happens, but that is from these solar winds. Um, when we have solar storms, we know that it affects us. It interferes with satellites. It causes planes to alter their routes because of those solar flares. It can cause damage to spacecraft, and it can also cause power outages. So the solar storms, so when we talk about solar flares, so that's the sun has a huge burst of these high energy particles that are concentrated, and they're coming out faster than the solar winds typically do. We can have some problems that arise from that. And something that I learned today when I was looking up things about the solar flares was that NASA has found that just like the Earth has magnetic field, so does the sun. The sun's magnetic field flips every 11 years. Earth's magnetic field, we're saying it's like 250,000 years between flips. The sun, it's every 11 years. And what NASA is now saying is that when the sun's magnetic field is aligned with Earth's magnetic field, that's when we get the most damage from the solar winds. So that's all new information, fairly new within the last 2, 3 years. Um, so that's all I have to say about Earth's magnetic field. Let me see if we have some questions. When are you going to post the lab? I'm going to try, I will post it tonight. So by the time you get up in the morning, it will be posted. Okay. Um, I'm still waiting on 2 videos from one of the teachers, but if I don't get it by tonight, I'll post it anyway, okay? So any other questions? All right, well, have a good week. I'll see you Friday. Friday, I think I'll just go over a few examples of electromagnetism. I really don't have anything new to present. All right, thank you. Have a good day. Have a good rest of your week. Okay.